Every night, something very strange happens. You willingly allow yourself to disappear. Not from the room, of course. Your body remains where you left it, resting beneath a blanket, surrounded by familiar walls, familiar sounds, and the quiet objects of an ordinary night. But your awareness of all of this begins to loosen. You close your eyes. The ceiling is no longer visible. The shape of the room fades from importance. Sounds that seemed clear a few minutes ago begin to drift farther away. Thoughts become less orderly, and then, without noticing the exact moment when it happens, you stop being consciously present for several hours of your own life. Later, you wake. Perhaps morning light has reached the curtains. Perhaps an alarm is sounding. Perhaps you simply open your eyes for no obvious reason. Several hours have passed, and yet your direct memory of those hours may contain almost nothing. This is one of the strangest ordinary experiences in human life. Night after night, the mind seems to vanish from the continuous story of the day, while the brain and body continue doing an extraordinary amount of work in the background. Sleep is not a simple biological off switch. Your brain does not become silent. Your organs do not stop regulating themselves. Your senses do not become completely disconnected. Instead, your entire nervous system moves into a different set of states, each with its own patterns of electrical activity, muscle tone, breathing, temperature, hormones, awareness, and memory. And the transition begins before you are fully asleep. As you settle into bed, your brain is still operating in waking mode. You remain responsive to the room around you. You can choose to move your hand, change position, listen to a distant sound, or continue a thought. But gradually, the balance begins to shift. Your eyelids remain closed for longer. Attention becomes less firmly attached to the outside world. Thoughts start wandering in unusual directions. The clear, organized flow of waking consciousness becomes softer and more fragmented. This borderland between wakefulness and sleep can produce some surprisingly strange experiences. You may begin imagining brief scenes that seem almost dreamlike, even though you still feel partly awake. A face may appear for a moment. A voice may seem to speak. A place you were thinking about may briefly become vivid. These experiences are sometimes called hypnagogic imagery. They are not quite ordinary waking thoughts, and they are not always fully developed dreams. They belong to the unstable transition in which the brain is gradually changing the way it processes both internal images and external sensations. During the same period, something even more dramatic can happen. Just as you begin drifting away, your body may suddenly jerk. A leg kicks, an arm twitches. Your shoulders jump, and sometimes the movement arrives together with the vivid sensation that you are falling. For a fraction of a second, you may feel as though the bed has disappeared beneath you, even though you have not moved anywhere at all. This is known as a hypnic jerk, or sleep start. These sudden movements are extremely common, and their exact cause is not completely settled. They appear to be linked to the nervous system's transition from wakefulness into sleep, when muscle activity and motor control are changing rapidly. They may become more noticeable during periods of stress, sleep deprivation, or stimulant use, but they can also occur during completely ordinary nights. The strange feeling of falling may simply be the dreaming brain constructing an explanation for a sudden burst of movement. or the sensation and the movement may arise together from shifting activity in the nervous system. Either way, it is a curious moment in which the body briefly interrupts its own descent into sleep. As the transition continues, you enter the lightest stage of non-REM sleep. This stage can be so shallow that you may not feel as though you were asleep at all. If someone wakes you after only a few minutes, you might insist that you were still awake. But your brain has already begun changing. The electrical rhythms measured at the scalp become slower than during alert wakefulness. Your awareness of the room weakens. Your muscles relax further. Eye movements become slower. The outside world has not disappeared, but it is becoming less important. This creates an unusual situation. Your brain must allow you to become disconnected enough to sleep, while still remaining capable of noticing something important. It cannot treat every sound as an emergency. If it did, a refrigerator humming, distant traffic, rain against a window, or a partner shifting in bed would repeatedly wake you. So the sleeping brain begins filtering. Many ordinary sounds are reduced in importance, yet some signals can still pass through. A sudden, unfamiliar noise may wake you. A baby's cry may wake a sleeping parent more readily than another sound of similar volume. Your own name may produce more brain activity than a meaningless word, even when you do not fully awaken. Sleep, then, is not complete sensory isolation. The brain continues listening selectively. It keeps a kind of quiet watch over the environment while allowing conscious awareness to retreat. Soon, the brain settles more deeply into non-REM sleep. One of the most distinctive events of this period is the appearance of brief bursts of electrical activity known as sleep spindles. They last only a short time, often around a second or two, but they appear repeatedly throughout the night. To an observer looking at an EEG recording, they resemble sudden clusters of faster waves emerging from slower background activity. Sleep spindles are associated with communication between the thalamus and the cerebral cortex, two major parts of the brain involved in processing information. They may help reduce the impact of external sensory signals during sleep, making it less likely that every small noise will reach full awareness. They have also been linked to aspects of memory processing and learning. The exact details are still being studied, but one thing is clear. Even while you seem peacefully motionless, the sleeping brain is producing carefully organized patterns of activity. Another pattern appears during this stage as well. These are called K complexes. A K complex is a large, distinctive wave that can occur spontaneously or in response to a sound. It is almost as though the brain briefly acknowledges something in the environment, considers it, and then decides whether waking is necessary. Sometimes the result is that you remain asleep. The outside sound occurred. Your nervous system noticed, but your conscious mind never learned that it happened. And so, only a short time after closing your eyes, you have already entered a remarkably strange condition. Your muscles are relaxing. Your awareness of the room is fading. Your brain is producing new electrical rhythms. Small sounds are being filtered. Important signals are still being monitored. Sudden body movements may appear without warning. Dreamlike images can form before full sleep has even arrived. And all of this may happen without leaving a single lasting memory. You may think that sleep begins when nothing is happening anymore. But biologically, the opposite is closer to the truth. The moment you stop noticing the night is often the moment an entirely different kind of activity begins. And as sleep deepens, the changes become even more unusual. As sleep deepens, the night begins to feel quieter from the inside. The brain moves farther away from the fast, irregular activity of waking consciousness and towards slower, more synchronized rhythms. Large groups of neurons begin changing their activity together, producing the slow waves that are especially characteristic of deep non-REM sleep. These waves are remarkable because they reveal that the sleeping brain is not simply inactive. Instead, many neurons alternate between more active and less active states in a coordinated pattern. Across the cortex, millions of cells can briefly become quieter together, then become active again. Seen electrically, this creates broad, powerful waves that move through the sleeping brain. From the outside, you may appear almost completely still. Inside, however, vast populations of neurons are moving through an organized rhythm. This stage is often called slow-wave sleep, and it is usually most concentrated during the earlier part of the night. That distribution is not accidental. Sleep is regulated partly by a pressure that builds the longer you remain awake. The longer the brain has gone without sleep, the stronger the drive for deep sleep tends to become. After you finally fall asleep, some of that accumulated pressure begins to decrease. So the first few sleep cycles often contain more deep non-REM sleep than the later ones. This means the architecture of the night changes as the hours pass. The first part of sleep is not biologically identical to the final part. While the brain is entering these deeper states, your body is changing as well. One of the most important shifts involves temperature. Your core body temperature generally falls during the night. This decline begins around the usual sleep period and is linked to the body's circadian timing system. Curiously, falling asleep often involves moving heat away from the body's core. Blood vessels near the skin, especially in the hands and feet, can widen, allowing more heat to escape into the surrounding environment. So warm hands and feet can actually accompany a cooling core. It may seem contradictory, but the body can feel comfortably warm at the surface, while its internal temperature is gradually decreasing. This is one reason the thermal environment matters so much during sleep. A room that is excessively hot can interfere with the body's normal ability to lose heat. And although individual comfort varies, the sleeping body generally needs to maintain a delicate balance between warmth and cooling. Under a blanket, another subtle process is taking place. The space close to the skin develops its own small, stable climate. The blanket reduces rapid changes in temperature and limits heat loss enough to keep the skin comfortable, while the body's internal temperature follows its nightly rhythm. The comforting sensation of being covered may also reduce the need for frequent adjustments to changing air temperature. Even while deeply asleep, however, you do not remain in exactly the same position. People turn, shift, stretch, bend a knee, move an arm, or roll from one side to another many times during an ordinary night. Most of these movements leave no memory. They may occur around transitions between sleep stages, or during brief increases in brain activity that never become full awakenings. Changing position also helps prevent prolonged pressure on the same areas of the body. Your sleeping brain does not consciously think, "This shoulder has been compressed for too long." Yet sensory information from the body continues to arrive, and movement can occur without a fully awake decision. This is another strange feature of sleep. Complex adjustments can happen while the person who is making them has no awareness that they occurred. At the same time, cardiovascular activity generally becomes calmer during non-REM sleep. heart rate often slows, blood pressure usually falls. The autonomic nervous system shifts toward a state in which the parasympathetic system, associated with rest and maintenance, becomes more influential. These changes are not perfectly smooth. The heart does not become a metronome, and blood pressure does not remain at one fixed nighttime level. Small fluctuations continue. Brief awakenings, body movements, breathing changes, and transitions between sleep stages can all produce temporary shifts. But compared with active wakefulness, deep non-REM sleep is usually a quieter cardiovascular period. Breathing changes too. During stable non-REM sleep, breathing often becomes slower and more regular than it is during waking life. When awake, respiration is constantly influenced by speech, movement, emotion, deliberate control, and changing attention. During sleep, many of those influences fade. Automatic brainstem systems become even more dominant. They continue adjusting breathing according to the body's need for oxygen and the accumulation of carbon dioxide. This means that one of the most essential movements of your body continues all night without conscious supervision. You do not have to remember to breathe. You do not have to schedule the next breath. The nervous system quietly handles it. While awareness is absent, other automatic functions also shift. Saliva production generally decreases during sleep because you are not speaking, eating, or continually moving the mouth. The oral environment becomes different from daytime conditions. Swallowing also becomes less frequent, yet it does not disappear completely. The body continues performing occasional protective and maintenance movements without requiring conscious attention. Digestion, too, continues in the background. The digestive system does not shut down when you fall asleep. Its activity changes according to circadian rhythms, nervous system state, recent food intake, and hormonal signals. Some digestive processes slow, while others continue steadily through the night. Food eaten earlier is still being moved, broken down, absorbed, and processed long after you have stopped thinking about it. Meanwhile, your kidneys are participating in the nighttime transformation. For many people, urine production decreases during sleep. One important reason is a nighttime rise in antidiuretic hormone, also known as vasopressin. This hormone helps the kidneys conserve water, reducing the amount of urine produced over several hours. Without such regulation, uninterrupted sleep would be much more difficult. The sleeping body is, in a sense, adjusting its internal plumbing to fit the long period when you are unlikely to drink or visit the bathroom. Another hormonal rhythm becomes especially prominent during the early night. Growth hormone is often released in pulses associated with deep sleep, particularly during the first part of the sleep period. Despite its name, growth hormone is not important only in children. In adults, it remains involved in metabolism, tissue maintenance, and other restorative processes. Its secretion follows a complex rhythm, and sleep is one of the major influences shaping that pattern. So while you're unaware of the room, the body is not merely waiting for morning. It is changing temperature, regulating circulation, adjusting breathing, conserving water, modifying hormone release, repositioning itself, coordinating slow electrical rhythms across the brain, and performing countless small acts of internal maintenance that require no conscious instruction at all. Perhaps the strangest part is how little of this you ever notice. From your own point of view, deep sleep may feel like nothing, no duration, no movement, no effort, no awareness. But inside that apparent emptiness, the body is following one of the most structured biological programs it performs each day. And eventually, that deep quiet begins to change again. The brain becomes more active. The pattern of breathing becomes less predictable. The eyes prepare to move, and the muscles are about to enter one of the most unusual states of the entire night. Eventually, the deep quiet of non-REM sleep begins to loosen. The brain does not simply remain in one state until morning. Instead, sleep changes in repeating cycles, usually moving to lighter and deeper non-REM stages before entering a very different state known as REM sleep. REM stands for rapid eye movement. The name sounds simple, but the state itself is remarkably unusual. During REM sleep, the electrical activity of the brain becomes more similar in some ways to waking activity. Certain regions become highly active. Breathing becomes less regular. The eyes begin moving rapidly beneath the eyelids, and yet, at the same time, most of the skeletal muscles of the body become strongly inhibited. The brain becomes active while the body becomes unusually still. This combination is one of the strangest features of normal human sleep. The temporary reduction in muscle activity is often called REM atonia. It is produced by brain circuits that suppress many motor signals before they can reach the large muscles of the body. The effect is not absolute. The muscles involved in breathing continue working. The heart keeps beating. The eyes can move. Small twitches may still occur in the face, fingers, or limbs, but many of the muscles that would normally allow you to sit up, walk, reach, or run become much less available. This may help prevent the body from reproducing many of the movements taking place inside dreams. If you dream that you are climbing a staircase, swimming through water, or running down a road, the motor regions of the brain can still become active, but the signals normally capable of producing large movements are largely blocked. The dream body may be racing somewhere. The physical body may hardly move at all. This creates a remarkable separation between imagined movement and actual movement. Your brain can construct the experience of walking without your legs walking. It can generate the sensation of turning your head while your head remains on the pillow. It can create an entire moving world while the room around you stays almost unchanged. The eyes are an exception. During REM sleep, they often move quickly from side to side or in other directions beneath the closed eyelids. These movements gave the stage its name, but their exact relationship to dreams is more complicated than the old idea that the eyes are simply watching dream scenes like a movie. Research suggests that some rapid eye movements may relate to changes in internally generated visual processing, but dreams do not work like ordinary vision projected onto an inner screen. The sleeping brain is constructing experience from within. Visual areas may become active without receiving the normal stream of information from open eyes. A street, a forest, a childhood room, or a completely invented place can appear vivid, even though almost no light is reaching the retina. This is one reason dreams are so strange. The brain normally depends heavily on sensory information from the outside world. During dreaming, it can create convincing environments using internally generated activity instead. And those environments can feel remarkably real. In a dream, you may speak with someone who is not actually present. You may walk through a building that has never existed. You may accept impossible changes in location or time without finding them particularly surprising The critical reflective parts of waking thought do not operate in exactly the same way during REM sleep. Some brain systems involved in emotion, imagery, and memory can be highly active, while aspects of deliberate reasoning and reality checking may be altered. This helps explain why dream logic can feel perfectly ordinary while the dream is happening. A doorway may suddenly lead to a different city. A person may change identity halfway through a conversation. A familiar house may contain rooms that have never been there. While awake, such contradictions would immediately demand explanation. During a dream, they may pass without question. Dreams are not limited to REM sleep. Dream-like experiences can occur during non-REM sleep as well. But REM dreams are often described as especially vivid, emotional, visual, and story-like. And as the night progresses, REM periods tend to become longer. Early sleep usually contains relatively more deep non-REM sleep. Later sleep contains a greater proportion of REM. This changing pattern means that the final hours before waking are often especially rich in extended dream experiences. It may also help explain why a dream remembered in the morning can seem long and elaborate. You may have awakened directly from a later REM period, when the dream was still active enough to leave a temporary trace in memory. Yet even vivid dreams are often forgotten with surprising speed. A few seconds after waking, a dream may seem perfectly clear. You remember the location, the people, perhaps even the atmosphere. Then, almost immediately, details begin disappearing. Within minutes, what felt like a complete experience may be reduced to a few disconnected fragments. Dream forgetting appears to reflect several features of the sleeping brain. The memory systems that normally stabilize waking experiences are operating differently during sleep, and dream events are often poorly connected to the ordinary context that helps waking memories remain organized. If you do not mentally rehearse a dream soon after awakening, it may fade rapidly. This creates a peculiar situation. You may spend a significant portion of every night having experiences that you will never remember having. Entire imagined conversations may vanish. Landscapes may appear and disappear. Emotions may rise and dissolve. From the perspective of morning consciousness, those moments effectively never happened. But while they were occurring, they may have felt completely convincing. External reality is not entirely excluded from these dream worlds. A sound in the bedroom can sometimes become incorporated into a dream. A door closing might become thunder. Music playing quietly in the room might appear as music heard somewhere inside the dream. Someone speaking nearby may occasionally become a character speaking within the dream itself. Instead of immediately waking you, the brain may attempt to integrate the sensory signal into the ongoing internal experience. At other times, the same sound may wake you completely. Why one signal enters a dream while another causes awakening depends on many factors, including sleep stage, intensity, meaning, novelty, and the current state of the brain. Even in REM sleep, the outside world has not vanished. It has simply become less dominant than the world being generated from within. Breathing also becomes more variable during REM. Unlike the relatively regular pattern often seen in stable non-REM sleep, REM breathing can change from moment to moment. It may become shallower, faster, slower, or temporarily irregular. Heart rate can also become more variable. This does not mean the sleeping body is losing control. Rather, REM sleep has a different pattern of autonomic regulation. The internal physiology of the body becomes less steady than during deep non-REM sleep. And so, within a single sleep cycle, the body can move from slow synchronized brainwaves and relatively calm breathing into vivid internally generated experience, rapid eye movements, changing heart rate, and widespread muscle inhibition. Then REM ends. the cycle begins shifting again. Over the course of the night, this pattern repeats several times, but never in exactly the same proportions. Deep sleep gradually becomes less dominant. REM stretches longer. Dreams often become richer. And while morning slowly approaches outside the room, the sleeping brain continues moving between states that feel, from the inside, like entire different worlds. Not every transition during the night is smooth. Sometimes the sleeping brain does something especially peculiar. It becomes partly awake. Not fully awake in the ordinary daytime sense, and not fully asleep either. For a brief period, different systems in the brain can seem to occupy different states at the same time. This helps explain a family of unusual nighttime behaviors known as parasomnias. One of the simplest is sleep talking. A sleeping person may suddenly say a word, mumble a sentence, laugh softly, call out, or produce speech that sounds meaningful for a moment, and then dissolves into nonsense. In the morning, there may be no memory of it at all. Sleep talking can occur during different stages of sleep, and the content does not necessarily reveal hidden truths or deep secrets. Sometimes it is clear enough to understand. Sometimes it is only a few sounds. The important point is that parts of the brain involved in producing speech can become active without the rest of the mind returning to full waking awareness. Language can briefly escape from a sleeping brain. A more dramatic example is sleepwalking. Sleepwalking often arises from deep, non-REM sleep, especially during the earlier part of the night. The person may sit up, stand, walk through a room, or perform simple familiar actions while remaining only partially conscious. Their eyes may be open, they may appear awake, yet their awareness can be very limited. This seems almost impossible at first. Walking is a coordinated activity. It requires balance, posture, muscle control, and continuous adjustment. But much of that control does not depend on the fully reflective, self-aware state you experience during the day. The brain contains motor systems capable of carrying out familiar patterns with surprisingly little conscious supervision. During sleepwalking, some of those systems become active, while other networks involved in judgment, memory, and full awareness remain in a sleep-like state. It is a striking example of how consciousness is not simply one switch labeled awake or asleep. Different parts of the brain can wake unevenly. Related events are sometimes called confusional arousals. A person may sit up, look around, respond slowly, or seem puzzled by where they are. For a short time, the bedroom may not feel familiar. A question may be answered strangely. A person may try to perform an action that makes little sense. Then, after returning to sleep, the episode may leave little or no memory. These events tend to occur when the brain is trying to rise out of deep sleep, but does not complete the transition cleanly. It is as though waking has begun before the entire brain is caught up. Even ordinary awakenings contain a milder version of this. You may open your eyes in an unfamiliar hotel room and, for a few seconds, have no idea where you are. The ceiling looks wrong. The window is in the wrong place. Then memory returns. The brain reconstructs context. The room becomes understandable again. That brief confusion reveals something that is easy to forget during the day. Your sense of place is actively maintained by memory. When you awaken, the brain sometimes has to rebuild that sense before the world feels normal. Another strange state appears at the boundary between REM sleep and waking. You become conscious. You know you are in bed. You may hear the room around you. But for a short time, you cannot move. This is sleep paralysis. It happens when awareness returns, while the muscle inhibition associated with REM sleep has not yet completely disappeared. The mismatch can be unsettling if it is unexpected. But the underlying process is understandable. The brain systems supporting conscious awareness have awakened before the systems that restore ordinary voluntary movement. The paralysis usually resolves on its own as the transition finishes, because dream imagery can occasionally persist into this half-awake state. Some people also experience vivid sensations, sounds, or impressions of a presence in the room. These experiences can feel extremely convincing, but they do not require anything supernatural. They can arise when REM-related imagery overlaps briefly with waking perception. This is one of sleep's most remarkable border states. The real bedroom and internally generated dream material can temporarily exist in the same experience. A very different form of mixed awareness can happen when a person realizes that they are dreaming. This is called lucid dreaming. In an ordinary dream, the dream world is usually accepted as reality. In a lucid dream, something changes. Perhaps an impossible event draws attention. Perhaps the dreamer notices a contradiction, and suddenly there is a recognition. This is a dream. Lucid dreaming has been studied in sleep laboratories, including through predetermined eye movement signals made by dreamers during REM sleep. That does not mean every claim about controlling dreams is scientifically established. Lucidity varies greatly. Some people can influence parts of a dream, while others may simply become aware of the state without controlling much at all. Still, the phenomenon demonstrates that a degree of reflective awareness can sometimes appear inside sleep. The mind can, in a limited sense, notice its own dream while the dream is still unfolding. Then there are false awakenings. You dream that you have awakened. You may get out of bed. You may look around your room. You may begin what seems like an ordinary morning. Only later do you discover that you never actually woke up. Sometimes a person even dreams of waking more than once. The experience is strange because waking itself has become part of the dream. The brain has constructed not a fantasy landscape, but a convincing simulation of returning to reality. This tells us something subtle about everyday consciousness. The feeling of being awake is itself partly a state the brain generates. Usually that state corresponds accurately to the outside world. During a false awakening, the same feeling can be reproduced internally. These transitions between sleep and waking are not failures of sleep. They are reminders that sleep is dynamic. The nervous system is constantly moving between levels of awareness, muscle control, sensory processing, and memory. Most nights, those changes happen so smoothly that you never notice them. But occasionally the borders become visible. Speech appears without full consciousness. Walking begins without ordinary awareness. Dream imagery lingers after waking. Awareness returns before movement, or a dream becomes aware of itself. And somewhere within all of these strange events is the same quiet lesson. Being asleep and being awake are not always perfectly separate worlds. Sometimes, for a few seconds, the brain stands with one foot in each. While the sleeping brain moves through its cycles, another hidden process is taking place. Experiences from the day are being handled differently from the way they were while you were awake. A conversation you barely noticed, a route you practiced, a new skill, a stressful moment, a face, a sound, a fact you tried to remember. All of these may leave temporary traces in the nervous system. Sleep does not simply place those traces into storage. Memory is more complicated than that. Some memories become more stable. Some are reorganized. Some lose detail. Some become easier to retrieve. And some seem to fade. This is one reason sleep is so closely connected with learning. During waking life, the hippocampus plays an important role in rapidly forming memories of events and experiences. It helps bind together information about what happened, where it happened, and when it happened. But a newly formed memory is not necessarily permanent. It may initially be fragile, across time, and with the help of repeated reactivation, some of that information can become more integrated with longer-term networks across the cortex. Sleep appears to contribute to this process. One especially intriguing idea is that patterns of neural activity associated with recent experience can be reactivated during sleep. In animal research, neurons that were active while an animal moved through a particular environment have been observed firing again later during rest and sleep. In humans, the details are harder to observe directly, but a growing body of evidence suggests that recently learned information can also be selectively reactivated during sleep. The brain, in other words, may revisit traces of the day without replaying them as a perfect recording. That distinction matters. Memory is not a video archive. The sleeping brain does not simply rewind the day's events from beginning to end. Instead, fragments of recent experience may be reprocessed, reorganized, and connected with older knowledge. A memory can become stronger without becoming more detailed. Sometimes what remains after sleep is not every small feature of an event, but its structure, the important pattern, the relationship between ideas, the skill itself. This may help explain why something practiced before bed can occasionally feel easier the next day. Certain forms of learning, especially motor and perceptual learning, can improve after sleep even without additional practice. The fingers have not rehearsed the movement consciously during the night. The eyes have not repeated the visual task. Yet performance may become more efficient. Different sleep stages appear to support different aspects of memory, and the picture is still being refined. Deep, non-REM sleep is often associated with the stabilization and reorganization of declarative memories, such as facts and events. Sleep spindles have also been linked with learning and memory performance. REM sleep has been studied in relation to emotional memory, procedural learning, and integration, although many simple claims about one stage having one exclusive function are probably too neat. Memory processing seems to depend on interactions across the whole night. And perhaps the strangest part is that forgetting may also be useful. It is easy to think of memory as something that should always be preserved, but the brain encounters far more information than it needs to keep permanently. The exact position of every object you passed during the day, every meaningless background noise, every small visual detail, every repeated sensation of clothing against the skin. If all of these remain equally strong, memory would become crowded with information that had little future value. Sleep may contribute to selective weakening as well as strengthening. Some neural connections may become relatively less influential, while more important patterns are preserved. One influential family of theories proposes that sleep helps renormalize synaptic strength after the widespread learning and stimulation of waking life. The exact biological details remain under investigation, and it would be too simple to say that sleep merely deletes unnecessary memories. But there is good reason to think that forgetting is not always a failure. Sometimes losing detail helps the brain extract what matters. A memory of a particular room may gradually become less about the exact angle of a chair and more about the general structure of the place. A sequence of repeated experiences may eventually form a broader rule. The sleeping brain may help transform specific events into knowledge that can be used more flexibly later. Emotional memories are handled in their own complicated way. Events with strong emotional significance are often remembered better than neutral ones. During sleep, the brain may continue processing some of those memories, changing how strongly different parts of the experience are represented. This does not mean that one good night's sleep erases unpleasant emotions, nor does it mean that dreams automatically solve emotional problems. The relationship between sleep and emotional memory is much more subtle, but sleep does appear to influence the way emotional experiences are consolidated and the way the brain responds to emotional information the next day. After insufficient sleep, people often become more reactive to negative events. Ordinary frustrations may feel sharper. Emotional regulation can become more difficult. Part of this may reflect changes in communication between brain systems involved in emotion and those involved in regulation and decision-making. So, the sleeping brain is not only preserving yesterday, it is also quietly changing the way tomorrow may feel. There is another curious feature of memory during sleep. A person can sometimes learn that a sound has meaning without consciously waking, but the limits are important. The sleeping brain is not well suited to absorbing complex new material in the way an awake student can. Playing an entire language course beside the bed does not turn sleep into ordinary study time. Yet simple forms of conditioning and sensory association may sometimes occur under carefully controlled conditions. Even more interestingly, researchers have used sounds or odors previously associated with learned material to influence which memories are reactivated during sleep. This technique, often called targeted memory reactivation, does not implant entirely new memories. Instead, it may gently bias the sleeping brain toward material that was already learned while awake. The effect is generally modest and depends on timing, sleep stage, and the type of memory involved. Still, the idea is remarkable. A quiet cue from the outside world can sometimes reach the sleeping brain and nudge the processing of something learned hours earlier. All of this happens while subjective time has nearly vanished. You do not feel memories being reorganized. You do not sense one neural pattern becoming more stable than another. You do not notice some details fading while broader connections strengthen. Morning simply arrives, and the brain that wakes is not quite the same brain that went to bed. It carries a slightly altered version of yesterday. Some experiences are easier to retrieve. Some skills are more settled. Some details are weaker. Some associations have changed. Sleep has edited the past without asking for conscious permission. And as those memories shift quietly in the background, another hidden system is also becoming more active. One concerned not with remembering the day, but with maintaining the physical environment in which all those memories exist. While memories are being reshaped, the brain itself is also being maintained. This is one of the quieter mysteries of sleep. The brain is extraordinarily active during the day. Neurons send electrical signals, exchange chemical messages, alter their connections, and consume large amounts of energy. Like any active tissue, the brain also produces metabolic byproducts. For many years, researchers wondered how this delicate organ manages the physical consequences of so much activity. One important clue came from the movement of fluid through and around brain tissue. The brain is surrounded by cerebrospinal fluid, a clear liquid that cushions the central nervous system and helps maintain a stable chemical environment. During sleep, especially during deep non-REM sleep, the movement of this fluid appears to change. In animal studies, researchers have observed increased exchange between cerebrospinal fluid and the spaces surrounding brain cells during sleep. This has been associated with a process sometimes called the glymphatic system. The name refers to a network of fluid movement involving glial cells, which support and surround neurons. The basic idea is that sleep may create conditions that improve the movement of fluid through brain tissue, helping transport certain metabolic waste products away. This has attracted enormous attention because it suggests that sleep may contribute to physical housekeeping inside the brain. But it is important to keep the claim in proportion. The glymphatic system is strongly supported by animal research, while its exact role, scale, and timing in humans are still being actively studied. Human brains are larger, more complex, and harder to observe directly. So it would be too simple to imagine deep sleep as a kind of automatic washing cycle. Still, the larger picture is fascinating. Sleep appears to change the physical environment around brain cells in ways that may support clearance and maintenance. And those changes may be linked to the slow electrical rhythms already unfolding across the cortex. Recent human imaging studies have shown that deep sleep can be accompanied by large, slow fluctuations in blood flow and cerebrospinal fluid. Neural activity, blood volume, and fluid movement seem to interact in a coordinated rhythm. So a slow brainwave is not only an electrical event, it may be accompanied by broader physical changes moving through the brain. While the brain is undergoing this nightly maintenance, the rest of the body is doing something similar on a much larger scale. Sleep provides a biological setting in which repair, immune regulation, protein synthesis, and cellular maintenance can proceed under different conditions from waking life. The body does not wait until sleep to repair itself. These processes happen all day, but many of them follow daily rhythms. And some are influenced strongly by sleep. The immune system is a good example. During sleep, levels of certain signaling molecules change. Some immune cells alter their activity and movement through the body. Communication between the nervous system and immune system continues throughout the night. This does not mean that sleep simply turns the immune system on. The relationship is much more complex. Some aspects of immunity become more active, others are redistributed, and inflammatory signaling follows its own circadian patterns. Sleep and immunity influence each other in both directions. When the immune system is responding to infection, it can change sleepiness and sleep structure. And when sleep is repeatedly restricted, aspects of immune regulation can also change. This connection may be one reason illness often produces a powerful desire to sleep. The body is entering a state in which energy use, behavior, temperature regulation, and immune signaling are being adjusted together. Even ordinary nights involve quieter versions of this coordination. At the cellular level, repair never truly stops. Proteins that have been damaged can be replaced. Cell membranes are maintained. DNA repair mechanisms continue working. Tissues respond to the small stresses created by normal activity. Again, sleep is not the only time these things happen. But sleep changes the hormonal and metabolic environment in which they occur. The nighttime body is not simply resting. It is operating under a different biological schedule. One especially interesting change involves energy use. The brain remains metabolically active during sleep, but different regions change their activity in different ways. Some areas reduce their energy demands during deep sleep. Others become more active during REM. Across the body, insulin sensitivity, glucose regulation, and other metabolic processes also follow strong daily rhythms. The timing and quality of sleep can influence these systems, which is one reason sleep is closely connected with overall metabolic health. Yet from the sleeper's point of view, none of this feels like work. There is no sensation of cellular repair, no awareness of immune cells changing location, no feeling of fluid moving around the brain. These processes happen beneath the level of experience. Another hidden change occurs in the way the sleeping brain processes touch and discomfort. Sensory signals from the body do not stop traveling. Pressure from the mattress still reaches the nervous system. A blanket still touches the skin. A limb that remains in an awkward position still sends information, but those signals are less likely to become full conscious experiences. The sleeping brain changes how sensory information is gated and interpreted. This helps explain how a person can remain asleep despite continuous contact with sheets, clothing, pillows, and the mattress. The sensory world has not disappeared. It has been given a lower priority. Pain perception also changes during sleep, though not in a simple way. Sleep can reduce conscious awareness of some mild sensations, but significant discomfort can still disturb sleep or trigger awakening. And the relationship works in the other direction too. Poor sleep can increase pain sensitivity the following day. The boundary between sleep and sensation is therefore flexible rather than absolute. The brain is constantly deciding, in a manner far below conscious thought, what information can be ignored and what deserves attention. Temperature is treated in a similar way. A slight change may pass unnoticed. A larger shift may cause movement. The foot emerges from beneath the blanket. The body curls more tightly. A hand pulls the covers closer. None of these adjustments require a fully awake decision. The sleeping nervous system is still controlling posture and responding to the environment. This creates another quiet paradox. You are least aware of your body at the very time when the body is continuously monitoring itself. Pressure is detected, heat is redistributed, fluid balance is regulated, cells maintain their internal machinery. Immune signals rise and fall. The physical environment of the brain changes with the rhythm of sleep, and most of it takes place without becoming part of a dream or a memory. Hours later, you may wake with the feeling that nothing happened. But beneath that blank interval, the body has spent the night performing countless small acts of maintenance. Some are ancient and well understood. Others are still being investigated. And as the night continues, another system becomes increasingly important. The airway softens. The throat changes shape. Breathing becomes more vulnerable to vibration and obstruction, and the quiet act of sleeping can suddenly become audible. Once breathing becomes audible, another hidden side of sleep begins to reveal itself. During the day, the upper airway is held open, partly by the activity of muscles in the tongue, soft palate, and throat. These tissues do not simply sit there. They are constantly being adjusted by the nervous system. When you fall asleep, some of that muscle tone decreases. The airway becomes slightly narrower and more flexible. For many people, air still moves through easily, But in others, the softer tissues begin to vibrate as air passes. That vibration is snoring. The sound may be soft and steady, or rough and irregular. It can change with body position, sleep stage, nasal congestion, anatomy, and how deeply a person is sleeping. What is strange is that the person producing the sound often has no idea it is happening. A sleeper may generate enough noise to wake someone else in the room, while remaining completely unaware of it. The brain is creating the sound, in a sense, by allowing the airway muscles to relax, yet the same brain may filter that sound out. This is possible because self-generated and familiar sounds are often treated differently from sudden, unfamiliar ones. The sleeping brain is not simply measuring volume. It is evaluating relevance. A quiet, unusual noise may provoke an awakening, while a louder, repetitive sound may eventually be ignored. Breathing becomes even more unusual during REM sleep. Because muscle tone is reduced more strongly during REM, the tissues of the upper airway can become less stable. At the same time, breathing itself becomes more variable. The result is a stage in which airflow, muscle control, and the sleeping brain's response to changes in oxygen and carbon dioxide are all interacting moment by moment. In some people, the airway can become partially or repeatedly obstructed during sleep. When that happens frequently, it may form part of a sleep-related breathing disorder. But even in ordinary sleep, the airway is never entirely passive. The nervous system continues sensing changes in breathing. If airflow becomes inadequate, protective mechanisms can increase respiratory effort or briefly shift the brain toward a lighter level of sleep. These reactions can be so short that the sleeper does not remember waking. A night can therefore contain tiny arousals that barely reach consciousness. For a few seconds, brain activity moves toward wakefulness. Muscle tone increases, breathing stabilizes, and then sleep resumes. From the sleeper's perspective, the night may still feel continuous. This reveals another odd property of memory during sleep. You can wake briefly without remembering that you woke. Not every awakening becomes part of autobiographical memory. A person may change position, open their eyes, adjust a pillow, or respond to discomfort and have no recollection of it the next morning. Sleep is full of these missing moments. Some nights may contain many brief transitions that disappear entirely from memory. Another nocturnal behavior can occur much closer to the mouth. The jaw may begin moving. The teeth may press together. Sometimes they grind. This is known as sleep bruxism. It does not necessarily happen continuously through the night. Instead, episodes often occur in brief bursts, sometimes around changes in sleep depth or short arousals. The jaw muscles become active for a moment, even though most voluntary movement remains reduced. What makes this particularly curious is that the action can be surprisingly forceful. During the day, you would probably notice immediately if you were clenching your teeth. During sleep, the same muscular activity may pass entirely outside awareness. The sleeping brain is capable of activating a specific motor system without restoring ordinary consciousness. The mouth, throat, eyes, fingers, and limbs can each show small islands of movement, while most of the body remains deeply asleep. Even the nose plays a changing role over the course of the night. Nasal airflow is influenced by congestion, body position, humidity, and the natural nasal cycle. The nasal cycle is a normal pattern in which one side of the nose becomes somewhat more congested, while the other becomes more open. Then the balance gradually reverses. Most people hardly notice this while awake. During sleep, it continues quietly in the background. Changing position may influence it as well. Lying on one side can increase congestion in the lower nasal passage, while the upper side becomes more open. So even the route air takes through your nose may shift while you sleep. The throat has another small nighttime task. Swallowing becomes less frequent than during wakefulness, but it still occurs. Saliva, mucus, and small secretions must occasionally be cleared. These swallows can happen without waking you. They require coordination among muscles in the tongue, pharynx, and larynx, all while breathing is briefly interrupted in a carefully timed sequence. The sleeping nervous system is therefore performing a quiet choreography. Breathe, pause, swallow, resume breathing. Most nights, this happens automatically and repeatedly. The same protective coordination helps keep material from entering the airway. Sleep reduces some reflexes, but it does not eliminate them. Coughing, swallowing, and airway responses can still occur when the nervous system decides that something requires attention. Another strange phenomenon involves sound itself. A sleeper may sometimes produce a sigh. This is not necessarily an emotional sigh. Periodic deeper breaths are part of normal respiratory regulation. A larger breath can help reopen small areas of the lungs and reset the pattern of breathing. During sleep, these sighs may appear without any corresponding dream emotion. The body is adjusting ventilation mechanically. To someone listening nearby, it may sound as though the sleeper is expressing relief, sadness, or exhaustion, but the breath may have no psychological meaning at all. This is one of the easiest mistakes to make when watching someone sleep. Many nighttime behaviors look expressive. A face moves, a person smiles, the eyebrows tighten, the jaw shifts, a sigh escapes. It is tempting to imagine an elaborate dream behind every movement. Sometimes there may be one, but often the cause is much simpler: a reflex, a breathing adjustment, a brief arousal, a small burst of motor activity. The sleeping body is full of actions that look meaningful from the outside while requiring no conscious story inside. And throughout all of this, the brain continues guarding the balance between stability and responsiveness. Too much responsiveness would make sleep impossible. Too little would leave the body unable to react when something truly matters. So the sleeping nervous system remains in between. It ignores much. It notices some. It adjusts constantly. And it rarely tells you about any of it. By morning, you may remember only a dream fragment or the moment you opened your eyes. You will not remember the airway narrowing and widening, the small changes in breathing effort, the forgotten arousals, the jaw movements, the nasal cycle, the swallowing, the sighs. Yet all of them may have taken place in the long, quiet interval you experienced as almost nothing. And farther into the night, another kind of hidden rhythm is unfolding. Hormones that help prepare the body for darkness, restoration, and eventually morning are rising and falling with extraordinary precision. Long before morning arrives, the sleeping body begins preparing for it. This preparation is guided by rhythms that continue whether you are paying attention to them or not. One of the most familiar is melatonin. Melatonin is often described as a sleep hormone, but that description can be misleading if it makes the molecule sound like a chemical switch that forces the brain into unconsciousness. Its role is subtler. Melatonin is produced primarily by the pineal gland, and its release is strongly influenced by the daily cycle of light and darkness. Under ordinary conditions, levels begin rising in the evening as the biological night approaches. They remain elevated for much of the night, then decline again toward morning. Rather than causing sleep by itself, melatonin helps signal to the body that biological nighttime has arrived. It is part of the internal timing system that coordinates sleep with the 24-hour day. That timing system is centered in a small region of the hypothalamus called the suprachiasmatic nucleus. This group of neurons acts as a major circadian clock. It receives information about environmental light through pathways connected to the eyes and helps synchronize rhythms throughout the body. So even when your eyes are closed and you are no longer consciously seeing the room, the body is still operating according to information gathered about the larger cycle of day and night. The clock influences far more than sleepiness. Body temperature, hormone secretion, alertness, metabolism, and many other processes rise and fall according to daily patterns. Some of these rhythms reach their peaks while you are asleep. Others begin changing hours before you wake. This means morning does not begin when your eyes open. Biologically, morning has already been approaching for some time. One of the clearest examples involves cortisol. Cortisol is sometimes called a stress hormone, but it has important normal functions far beyond stressful situations. Its levels follow a strong daily rhythm. They are often relatively low during the early portion of the night, then begin increasing during the later hours of sleep. Near the usual waking period, cortisol rises more strongly, helping support the transition toward daytime activity. So, while you may still be dreaming, the endocrine system is gradually shifting the body toward wakefulness. Energy availability changes. Cardiovascular regulation begins moving toward daytime patterns. The chemistry of morning starts assembling itself before consciousness returns. This helps explain why waking is not simply the result of an alarm interrupting sleep. The body has its own expectation of when waking should occur. When sleep and circadian timing are regular, internal rhythms can become strongly aligned with a habitual schedule. Some people occasionally wake just before familiar alarm sounds. This does not require the brain to know the exact digital time in the way a clock does. Instead, a combination of circadian timing, learned expectation, sleep cycles, environmental cues, and rising morning arousal may bring the brain close to waking at roughly the expected hour. The precision is not perfect, but the phenomenon shows how strongly time can be represented biologically without conscious counting. Other hormones also follow sleep-related rhythms. Prolactin, for example, often rises after sleep begins and can remain elevated for much of the night. Thyroid-stimulating hormone follows its own circadian pattern, shaped by both sleep and internal timekeeping. Leptin and ghrelin, hormones involved in appetite regulation, are also influenced by sleep duration and timing. The endocrine system is not waiting passively for daylight. It is continuously adjusting. These signals help coordinate organs that are separated by large distances within the body. The liver, muscles, digestive system, fat tissue, and brain all contain clocks of their own. They are not independent in the absolute sense, but they can respond to timing signals such as light exposure, food intake, activity, and sleep. The result is less like a single clock and more like an orchestra of many clocks that normally remain synchronized. Sleep is one of the major behaviors around which this coordination is organized. When the sleep schedule shifts suddenly, as during jet lag or night work, these rhythms may not all move at the same speed. A person can feel tired at one time, hungry at another, and alert at a biologically inconvenient hour. That mismatch reveals how many separate processes are normally aligned quietly in the background. Even within one ordinary night, hormone release often occurs in pulses rather than as a smooth stream. The endocrine system frequently works in bursts. A gland releases more of a hormone for a period. Levels rise, then fall, and another pulse may appear later. This pulsatile pattern can carry information that would be lost if hormone levels remain constant. Sleep influences the timing of several of these pulses. Some are associated more strongly with particular sleep stages. Others follow circadian time even if sleep itself is disturbed. Separating the influence of sleep from the influence of the internal clock is one of the challenges of sleep research. Two events may happen at the same time every night without one directly causing the other. Researchers often study this by altering sleep timing, keeping participants awake, or controlling exposure to light and meals. These experiments reveal that the night is governed by overlapping systems. One system tracks how long you have been awake and how much sleep pressure has accumulated. Another tracks biological time. The two interact, but they are not identical. That is why you can sometimes feel deeply sleepy at night, even after a quiet day, or strangely alert late in the evening, despite having been awake for many hours. The body is combining several internal signals at once. Toward morning, this balance begins shifting. Melatonin falls. Cortisol rises. Core body temperature, after reaching its nighttime low, begins moving upward again. REM periods are often longer. Deep sleep has become less prominent. The sleeping brain becomes increasingly easy to awaken. Morning is slowly entering the body before it enters awareness. And yet, if you wake during this transition, it may still feel instantaneous. One moment, there was a dream. The next moment, there is a ceiling. You do not feel the hormones changing. You do not sense the circadian clock moving forward. You do not hear the body quietly preparing its systems for daylight. Consciousness simply returns near the end of a process that has been developing for hours. This may be one of the most elegant, strange things about sleep. The part of you that experiences the night is absent for much of it, but the body never loses track of where it is in time. Darkness is registered. Internal clocks continue ticking. Chemical signals rise and fall. Morning is anticipated, and all of it happens while your subjective sense of time has almost completely disappeared. One of the strangest things sleep does is remove almost all sense of duration. You may fall asleep at midnight and open your eyes several hours later. Yet the interval between those two moments can seem strangely compressed. There is usually no continuous feeling of having passed through 6 or 7 hours. Deep sleep especially may leave almost no subjective trace of time at all. From the inside, hours can disappear. This happens partly because the brain systems that create a continuous waking record of experience are operating differently during sleep. While awake, you constantly collect markers of time. You notice changes in light. You finish one thought and begin another. You walk from one room to another. You hear sounds in sequence. You remember what happened a few minutes ago and compare it with what is happening now. These continuous updates help create the feeling that time is passing. During much of sleep, that chain becomes fragmented. There may be dreams, brief arousals, movements, and changes in brain activity, but they are not usually stored as a stable sequence of memories. Without a remembered sequence of events, the interval can seem almost empty afterward. Time did not actually move faster. The brain simply failed to build the kind of record that normally gives several hours a feeling of length. Dreams complicate this further. A dream can seem to contain a long journey, an entire conversation, or a series of events that appear to unfold over a considerable period. Yet estimating dream duration is difficult. Some laboratory studies suggest that actions performed in lucid dreams can take roughly similar amounts of time to comparable waking actions, although the relationship is not perfectly consistent. Dream time is therefore not necessarily completely disconnected from real time, but memory can distort it. A short sequence may feel long because the dream implies that more time has passed than was actually experienced. You may dream that you have been somewhere for days without experiencing every minute of those imagined days. The brain can create a sense of elapsed time using narrative information alone. It does something similar while awake. A film can jump from morning to evening, and you instantly understand that hours have passed, even though only seconds passed for you. Dreams may use the same ability without requiring a conscious editor. Another peculiar experience can happen near sleep onset. A person may believe they were awake for much longer than they really were. Someone might feel that they spent an hour lying in bed thinking, while measurements of brain activity suggest that portions of that period contain genuine sleep. This mismatch is sometimes called sleep state misperception. It does not mean the person is imagining the experience. Light sleep can contain thought, like mental activity. And because the boundary between wakefulness and sleep is gradual, portions of early sleep may feel very similar to being awake. The brain may therefore enter sleep without generating a clear internal announcement that sleep has begun. This is why you usually cannot identify the exact second when you fall asleep. You can remember approaching sleep. You can remember waking afterward. But the transition itself often disappears. Waking can be just as strange. Opening your eyes does not always mean the brain has instantly returned to full daytime performance. For several minutes, sometimes longer, attention, reaction time, memory, and decision-making may remain impaired. This period is known as sleep inertia. It is the mental heaviness that can make a familiar room feel distant, a simple question seem unexpectedly complicated, or the first movements of the morning feel slow and automatic. Sleep inertia tends to be stronger under certain conditions. Waking from deep sleep can produce more pronounced grogginess than waking from lighter sleep. Being sleep deprived can also make it worse. The biological night matters as well. If someone wakes at a time when the circadian system strongly promotes sleep, the brain may be slower to reach full alertness. So 2 awakenings after the same number of hours of sleep can feel completely different. One morning, consciousness seems to return almost immediately. Another morning, waking feels like moving through fog. The difference may partly depend on what state the brain was in. At the moment sleep ended, this is especially noticeable when a person is awakened suddenly from deep non-REM sleep. For a short time, the brain may remain partially organized in the slow patterns that dominated moments earlier. Different regions appear to recover at different speeds. Some networks involved in basic sensory awareness can return before those responsible for higher level attention and executive control are operating normally. Waking like falling asleep is not a single switch. It is a transition. This can produce small mistakes that seem almost absurd a few minutes later. You may silence an alarm without remembering doing it. You may reach for an object that is not where you expect. You may momentarily misunderstand a simple sentence. You may begin a familiar morning routine before fully realizing that you are awake. These actions demonstrate how much behavior can be guided by habit. The brain does not require its highest level of reflective awareness to perform every familiar movement. Some routines can begin while consciousness is still assembling itself. There is another curious effect when waking from a vivid dream. For a few seconds, the emotional state of the dream may survive even after its story has collapsed. You may wake feeling amused, anxious, relieved, or strangely nostalgic before remembering what caused the feeling. Sometimes the emotion remains, while the dream itself disappears. The brain has preserved the mood longer than the narrative. This suggests that different elements of an experience can fade at different rates. A dream location may vanish first, then the conversation, then the faces. Yet a faint emotional tone may linger into waking life. The opposite can also happen. You may remember an image clearly, but feel none of the emotion that seemed so powerful while dreaming. Memory is being dismantled unevenly as waking consciousness returns. Sensory information then rapidly reclaims priority. The pressure of the pillow becomes obvious. Sounds from outside separate themselves from the dream. The temperature of the room returns to awareness. Light filtering through closed eyelids gains meaning. The brain begins rebuilding a model of the real environment. Within moments, the imagined world that seemed unquestionable is replaced by a familiar bedroom, and this replacement happens so naturally that it is easy to overlook how extraordinary it is. A few seconds earlier, the brain may have been generating an entire reality from within. Now it is once again anchoring experience to incoming information from the world outside. Night after night, you cross this boundary without needing to understand how. You lose track of hours. You pass through states you will never remember. You may dream through experiences that feel long and detailed. Then consciousness returns in stages, reconstructing place, time, and identity. The clock says that much of the night has passed. Your body shows that it has passed. The sky outside may show that it has passed. But to the part of the mind that remembers continuously, the missing hours can feel almost impossibly short. Sleep has not stopped time. It has simply hidden most of the evidence that time was passing. Even after the outside world has faded from awareness, the sleeping body continues responding to signals that rarely enter memory. Some of these responses are so subtle that they can only be seen with sensors. Others are surprisingly physical, and a few seem almost contradictory to the idea of rest. Consider blood flow. The brain does not receive exactly the same pattern of circulation throughout the night. As neural activity changes from one sleep stage to another, regional blood flow changes with it. During deep non-REM sleep, overall brain metabolism is generally reduced compared with quiet wakefulness, and activity decreases across many cortical regions. But REM sleep is different. Some parts of the brain become highly active, including areas involved in emotion, visual imagery, memory, and internally generated experience. Blood flow shifts accordingly, so while the sleeper lies almost motionless, circulation inside the brain is continually being redistributed to match changing patterns of neural activity. The brain is never simply receiving one fixed nighttime supply. It is changing its demands from stage to stage. The body's control of heat also becomes surprisingly different during REM sleep. During much of non-REM sleep, thermoregulatory mechanisms still operate in familiar ways. If the environment becomes cool enough, the body can adjust blood flow near the skin and make other responses that help conserve heat. If it becomes too warm, mechanisms for losing heat can become more active. But during REM sleep, some thermoregulatory responses are reduced. The body behaves, for short periods, as though its temperature control system has become less responsive. This makes REM especially dependent on the thermal environment surrounding the sleeper. A bedroom that is comfortably stable may pass unnoticed. A room that becomes very hot or very cold is more likely to disturb the night's architecture. This is a curious feature of REM. The brain can produce an elaborate dream world while temporarily becoming somewhat less capable of defending its preferred body temperature. The sleeper is mentally active but physiologically dependent on the shelter around them. Another hidden change involves sweating. Sweat production does not simply continue at the same level all night. It is influenced by temperature, sleep stage, autonomic activity, bedding, and the surrounding air. A person can wake and find that a pillow or sheet feels warmer or slightly damp without remembering ever feeling hot. The body responded during the night, but the sensation failed to become a lasting conscious event. Skin itself continues changing as well. Blood vessels near the surface widen and narrow as circulation is regulated. Pressure shifts as the body changes position. Moisture slowly accumulates and evaporates. Tiny muscles attached to hairs may respond to temperature. None of these processes require awareness. Your largest sensory organ spends the entire night in contact with the environment, while you are barely conscious of having a body at all. The eyes also continue living through their own nighttime physiology. Closed eyelids block most light, but not all of it. Bright light can still penetrate the lids enough to affect the visual system, which is one reason intense morning light may influence waking even before the eyes are fully open. At the same time, blinking largely disappears during sleep. During the day, every blink spreads tears across the surface of the eye. At night, the eyelids remain closed, reducing evaporation and helping protect the cornea without the need for frequent blinking. The eye has shifted from an active daytime maintenance pattern to a quieter nighttime one. Then, during REM, the eyeballs begin moving beneath those closed lids. A structure protected in darkness is suddenly moving repeatedly, while the rest of the face may remain almost still. Elsewhere in the body, REM can produce another physiological event that is often misunderstood. Blood flow to the genitals can increase during REM sleep. In males, this commonly produces erections during the night. In females, corresponding increases in genital blood flow can also occur. These responses do not necessarily mean that a person is having a sexual dream. They are strongly connected to the autonomic physiology of REM sleep itself. A completely ordinary or even nonsensical dream can occur at the same time. This is a useful reminder that the sleeping body's reactions do not always reveal the content of the sleeping mind. A physical response may be generated by the sleep stage rather than by the story of the dream. Small muscle twitches provide another example. Although most large skeletal muscles are strongly inhibited during REM, brief twitches can still appear. A finger moves. A corner of the mouth shifts. A toe flexes. An arm gives a tiny jerk. These movements are particularly common in infants, but also occur in adults. Researchers have studied whether such twitches may provide sensory feedback to the sleeping nervous system, perhaps contributing to the maintenance or development of motor circuits. That idea remains an active area of research. What is clear is that REM atonia is not perfect stillness. The body contains brief sparks of movement within a generally motionless state. Leg movements can also occur outside REM. Some sleepers experience repeated, stereotyped movements of the legs during the night. These may involve flexing the ankle, knee, or hip, and can happen without conscious awareness. Occasional movements are common and not necessarily meaningful. When repeated frequently and associated with sleep disruption, they can become clinically relevant. But a sleeping body does not need a disorder to move. Even healthy sleep contains a surprising amount of motor activity. The idea of lying perfectly still for 8 hours is mostly an illusion created by memory. The sleeping person may turn dozens of times, adjust limbs, briefly tense muscles, scratch an itch, pull at bedding, or reposition the head. Yet because these actions rarely form lasting memories, morning consciousness reconstructs the night as continuous stillness. There are other signals the brain handles differently depending on the sense involved. Smell, for example, is not a particularly reliable alarm during sleep. Odors can influence the sleeping brain and may sometimes alter dream experience. But many smells are less likely to produce immediate awakening than meaningful sounds. The auditory system remains especially useful for nighttime monitoring because sound can signal something happening beyond the closed eyes. This helps explain why alarm clocks usually rely on sound rather than scent. The sleeping brain seems to preserve a selective gateway to hearing, but even hearing is filtered according to context. Researchers studying sleeping participants have found that the brain can distinguish features of speech without producing full awakening. Familiar voices may be processed differently from unfamiliar ones. Meaningful patterns can sometimes trigger stronger responses than acoustically similar but irrelevant sounds. The sleeper does not need to understand a conversation consciously for the auditory system to notice that one signal is different from another. Sleep, therefore, contains a peculiar form of awareness. Without awareness, the ears receive, the brain compares. Autonomic systems react. Muscles occasionally move. Circulation shifts. Temperature regulation changes. Yet the conscious person remains absent from almost all of it. By morning, none of these events may survive as memory. The night feels empty because consciousness remembers so little, but the body's records would tell a different story. They would show waves of circulation, changes in heat loss, eye movements, tiny muscle bursts, shifts in skin temperature, variations in sensory processing, and physical responses that occurred without dreams needing to explain them. And this quiet complexity continues as the night's sleep cycles turn again, preparing the brain for another task that becomes especially important by morning, deciding what from yesterday should still matter when you wake. One of the easiest ways to imagine sleep is as a state that spreads across the entire brain at once. You are awake, then you are asleep. Every region, we might assume, crosses the border together, but the reality appears to be much less uniform. Even during ordinary sleep, different parts of the brain can show slightly different patterns of activity at the same moment. Sleep is a whole brain state, but it is also surprisingly local. Researchers studying electrical activity have found that slow waves can be stronger in some cortical regions than in others. The pattern can even reflect what the brain was doing during the previous day. If a particular network has been used intensely while learning or practicing a task, aspects of subsequent slow wave activity may become more pronounced in related areas. This does not mean that one small piece of the brain simply goes to sleep independently while everything else remains awake. Human sleep is far more coordinated than that, but it suggests that the sleeping brain is not one perfectly synchronized object. Its regions have histories of their own. Some have been working harder. Some have recently changed their connections. Some may require different amounts of recovery or reorganization. The night can reflect those differences. This idea becomes even stranger when we consider what happens to communication across the brain. During waking life, consciousness depends partly on distant brain regions, exchanging information efficiently. A sound reaches sensory areas. Attention selects it. Memory gives the context. Other networks determine whether it matters. A decision may follow. All of this requires information to move between systems. During deep sleep, that long-range communication changes. Individual regions can remain electrically active, but their ability to participate in the highly integrated patterns associated with waking consciousness becomes reduced. The brain is active, yet its activity is organized differently. This may help explain why a sleeping person can process a sound without becoming consciously aware of it. A sensory area may respond. The signal may even influence later brain activity. But the information does not necessarily spread through the broader network strongly enough to create the rich, connected experience of hearing something while awake. Awareness requires more than electrical activity. It requires activity to be shared in the right way. The thalamus plays an important part in this changing relationship with the outside world. Almost all sensory information headed toward the cerebral cortex passes through thalamic circuits. During sleep, those circuits change their firing patterns. The thalamus does not simply close a door. Instead, its mode of communication changes. This contributes to the reduced influence of incoming sensory information and supports the rhythmic activity characteristic of non-REM sleep. A signal from the room can still arrive, but reaching the brain and reaching consciousness are not the same thing. Touch offers a simple example. Your sheets remain against your skin for hours. The mattress presses continuously against your body. Your head rests against the pillow. Yet after you fall asleep, you do not experience these sensations as an endless stream of touch. The receptors continue sending information. Some processing continues. But repeated, predictable signals lose access to awareness. If the pressure suddenly changes, however, the situation may be different. A limb shifts. Something brushes the skin unexpectedly. The mattress moves. A stronger or more novel signal may produce a brief arousal. The sleeping brain seems especially interested in change. Predictability is easier to ignore. This principle appears across several senses. A steady background sound may fade into the night. A sudden interruption of that sound may be more noticeable than the sound itself. Someone who falls asleep beside a humming fan may remain asleep while it continues, yet awaken when the electricity stops and the room becomes unexpectedly quiet. Nothing became louder. The important event was a change in expectation. The sleeping brain had built a model of what the environment was supposed to sound like. When reality violated that model, attention briefly increased. This ability may be one reason humans can sleep in relatively noisy environments after becoming accustomed to them. The brain learns what belongs. A train passing at roughly the same time each night may gradually become ordinary. Traffic outside, a familiar apartment may be filtered. But an unfamiliar knock or an unusual voice can still stand out. Sleep therefore contains a primitive form of prediction. The brain is not consciously thinking about what should happen next, yet it compares incoming signals with recent patterns. The expected can be reduced. The unexpected receives more processing. Not every response is large enough to wake you. Some produce what researchers call microarousals. These are very brief shifts toward wake-like brain activity that can last only seconds. A person may not open their eyes. They may not remember anything. They may not even visibly move. Yet, measurements show that the brain briefly became more activated. Heart rate can change at the same time. Muscle tone may increase. Then the system settles back into sleep. A supposedly uninterrupted night can contain many tiny changes of state. This is another reason the question, were you asleep or awake, is sometimes less simple than it appears. Sleep has depth. It has transitions. It has momentary disturbances. It has brief islands of increased responsiveness that disappear before memory can capture them. The autonomic nervous system also reveals these constantly shifting states. Heartbeats do not merely become slower at night. The timing between one beat and the next changes continuously. This variation is called heart rate variability. It reflects, among other influences, the changing balance between sympathetic and parasympathetic control. Across different stages of sleep, that balance shifts. Stable non-REM sleep often shows stronger parasympathetic influence. REM sleep can bring more irregular autonomic activity. Brief arousals can produce sudden increases in heart rate, even when the sleeper never remembers waking. So, the heart quietly records events that consciousness misses. Blood pressure can do something similar. For many people, it decreases during sleep compared with daytime levels. But the decline is not a perfectly smooth slope. Movement, arousal, REM activity, and changes in breathing can create short fluctuations. The cardiovascular system is continuously adjusting to the state of the brain. Even deep sleep contains variability. Nothing biological remains perfectly still. Perhaps that is the deeper pattern hiding beneath almost every strange feature of sleep. What looks simple from the outside is full of internal transitions. The brain is never asleep in exactly one way. Some regions produce stronger slow waves than others. Communication between distant networks changes. The thalamus alters the way sensory information is passed onward. Familiar sensations are suppressed. Unexpected changes are noticed. Tiny arousals appear and vanish. The heart responds to events that never become memories. And through all of it, consciousness remains only intermittently connected to what the body is doing. From the pillow, the night may seem like one continuous stretch of nothing. Inside the nervous system, it is anything but continuous. It is a landscape of shifting thresholds, changing rhythms, local differences, and brief moments when the outside world almost reaches you before fading away again. And as morning moves closer, those thresholds will begin changing once more, making the brain gradually more ready to return to the world it has been quietly monitoring all night. While the brain moves quietly through its changing rhythms, the rest of the body is also following a nighttime schedule that is easy to overlook. Many organs behave differently at night, not because they have stopped working, but because the conditions of sleep change what the body needs from them. The liver is one example. During the day, it is constantly responding to meals, movement, hormones, and changing energy demands. At night, especially during a long period without food, its priorities shift. It helps maintain a stable supply of glucose in the bloodstream so that tissues continue receiving energy even though you have not eaten for hours. The brain still requires fuel. The heart still requires fuel. Every sleeping cell continues using energy. So while you are unconscious, metabolism quietly changes from the pattern of the daytime feeding period toward the pattern of an overnight fast. This transition is partly controlled by the body's circadian clocks. Metabolism is strongly tied to time of day. The same meal can produce somewhat different metabolic responses depending on when it is eaten, because organs are not functioning identically across 24 hours. Sleep, therefore, takes place inside a much larger rhythm of feeding and fasting. The sleeping body knows, biologically, that this is usually the long interval when food does not arrive. Fat tissue participates as well. Stored energy can be released when needed, and hormones help determine whether energy is being stored, used, or conserved. These processes are not exclusive to sleep, but their balance changes across the night. And when normal sleep is repeatedly shortened, some of these metabolic signals can change in measurable ways. One effect involves appetite. After insufficient sleep, many people experience changes in hunger and food preference. The biology behind this is complicated and involves more than any single hormone. Brain reward systems, circadian timing, energy balance, and hormones involved in appetite regulation all contribute. This is a reminder that a night of sleep influences behavior that will not occur until many hours later. The sleeping body is already helping shape tomorrow's hunger. Muscles also spend the night in a state very different from daytime activity. During waking hours, even when you think you are sitting still, muscles continuously make tiny adjustments. They maintain posture. They stabilize joints. They hold the head upright. They prepare the body to move. Once you lie down and enter deeper sleep, much of this postural work becomes unnecessary. Muscle activity falls. The body no longer needs to resist gravity in the same way. A large amount of waking muscular effort quietly disappears. This is part of why lying down can feel so profoundly different from sitting. The skeleton is now supported by the bed, rather than constantly balanced by muscular tension. But reduced activity does not mean muscles become biologically inactive. They continue receiving blood. Proteins are still being built and broken down. Cells continue maintaining their internal structures. Hormonal conditions associated with sleep can support processes involved in recovery from normal daily activity. Sleep does not instantly rebuild a tired muscle, and physical recovery depends on nutrition, training, health, and many other factors. But adequate sleep forms part of the environment in which normal tissue maintenance occurs. Even bones are participating in nighttime biology. Bone may feel like a static material, but living bone is continuously remodeled. Specialized cells remove small amounts of old tissue, while others build new tissue. This process happens throughout life. It is influenced by hormones, mechanical loading, age, nutrition, and circadian rhythms. You do not feel bone remodeling while sleeping. There is no sensation that the skeleton is being maintained, yet beneath the stillness, even the hardest tissues in the body remain biologically active. The skin follows its own daily rhythm. Blood flow near the surface changes. Barrier function varies. Cell division and repair processes show circadian patterns. Water is continuously moving through and evaporating from the skin, even while you are asleep. This invisible loss of water is one reason the body must carefully manage hydration during the long overnight period. You may wake slightly lighter than when you went to bed, partly because water has been lost through breathing and the skin. No dramatic event occurred. Molecules of water simply left the body, little by little, for hours. Breathing itself contributes to this quiet loss. Nian. Every exhaled breath carries water vapor. Cold air can make this visible when you are awake outdoors, but in a bedroom, the same process usually remains unseen. Thousands of breaths take place during the night. Each one releases a tiny amount of moisture. By morning, the cumulative effect is measurable. Another system undergoing subtle changes is the digestive tract. Although digestion continues, movement through the gastrointestinal system generally follows strong daily rhythms. The colon, for example, is usually much less active during sleep than during daytime hours. Then, around waking and after the first meal, activity can increase sharply. The digestive system has, in effect, its own morning transition. This may help explain why certain bodily routines occur at predictable times after waking. The body is not starting them from nothing. It has been adjusting gastrointestinal activity throughout the night. The stomach also communicates with the brain during sleep. Stretch, acidity, and other internal signals continue to travel through nerves and chemical pathways. Most remain outside awareness, but a signal strong enough to matter can influence sleep depth or provoke awakening. Internal sensations therefore compete for access to consciousness, just as external sounds do. The brain does not only monitor the room, it monitors the body itself. This internal sense is sometimes described as interoception while awake. Interoception contributes to sensations such as hunger, heartbeat awareness, fullness, thirst, and the need to breathe more deeply. During sleep, much of this information is still being processed, but it rarely becomes conscious unless it crosses an important threshold. A bladder gradually filling through the night is a simple example. For hours, increasing stretch may be tolerated without waking. Eventually, if the signal becomes strong enough, it may enter awareness and end the current period of sleep. The same principle applies to thirst, temperature, breathing difficulty, and other bodily needs. The sleeping brain is not ignoring the body. It is raising the threshold for interruption. This creates a surprisingly sophisticated form of prioritization. Minor signals are allowed to remain in the background. Important ones are given greater access. The threshold also changes according to sleep stage. A sensation that would wake you from light sleep may fail to wake you from deeper sleep. The nervous system is constantly adjusting how difficult it is for the body to call consciousness back. Even itching is treated differently. During waking life, an itch can immediately capture attention and produce a scratch. During sleep, mild itching may never become conscious, but stronger stimulation can trigger a movement or partial arousal. A sleeper may scratch an arm or face and then continue sleeping without forming any memory of having done so. A purposeful-looking movement has occurred without ordinary purposeful awareness. Again and again, sleep reveals this strange separation. The body can detect, the body can decide, in a primitive neural sense, that a response is needed. The body can act, and the conscious mind may never know. By the later part of the night, the balance begins slowly shifting. Metabolic conditions have changed after hours without food. Water has been lost through skin and breath. The bladder may be fuller. Body temperature is beginning to rise from its nighttime low. Digestive systems are approaching their daytime pattern. Hormonal signals are preparing tissues for activity. The muscles that spent hours released from the work of posture will soon support the body again. None of these systems waits for the moment you decide to get out of bed. They begin preparing before you are aware that morning has arrived. And when your eyes finally open, what feels like the beginning of a new day is really the final step in a biological transition that began long before you knew anything was changing. There is another hidden process unfolding across the night that cannot be seen by watching a sleeping person. The brain is gradually reducing something that built up while they were awake. Sleep pressure. The longer you remain awake, the stronger the biological drive for sleep generally becomes. This pressure is one half of the system that determines when sleep feels difficult to resist. One chemical involved in this process is adenosine. Adenosine is produced through normal cellular activity and energy use. Across prolonged wakefulness, signaling to adenosine-related systems tends to increase, contributing to the growing feeling that the brain needs sleep. It does not act like sand collecting in a simple biological hourglass. Sleepiness depends on many interacting processes, but adenosine is an important part of the machinery that allows the nervous system to keep track, in a rough biological sense, of how long it has been awake. By late evening, the result may be familiar. The eyelids feel heavier. Attention becomes harder to hold. Motivation to remain active decreases. Quiet environments become unusually inviting. And once sleep finally begins, the pressure that accumulated during waking starts to decline. This is one reason sleep does not remain equally deep throughout the night. When the need for recovery is greatest, the brain tends to produce more intense slow-wave activity. As that need is gradually satisfied, the pressure for deep sleep decreases. The sleeping brain is therefore responding not only to the time shown by the circadian clock, but also to its own recent history. A brain that has been awake for an unusually long time does not enter the night in the same condition as one that has recently taken a long nap. Previous wakefulness leaves a measurable signature. After extended time awake, slow waves during subsequent sleep can become more powerful. Researchers sometimes describe this as increased slow-wave activity. The brain appears to emphasize deep non-REM sleep when sleep pressure is high. This does not mean every lost hour is later restored minute for minute. Sleep recovery is more complicated than simply adding back exactly what was missed. Instead, sleep structure can change. Certain features become more intense. Some stages may be prioritized. The brain adjusts the composition of the recovery period. This becomes especially clear after significant sleep deprivation. A person who has remained awake much longer than usual may fall asleep rapidly and enter deeper sleep more strongly than they normally would. The sleeping system seems to recognize that something is missing. It does not need a conscious memory of being tired. The pressure is built into physiology. REM sleep can show a different kind of recovery response. If REM sleep is repeatedly interrupted or selectively reduced, later sleep may contain more REM or may enter REM more readily. This phenomenon is often called REM, rebound. It does not happen in exactly the same way under all conditions, and many factors influence it, but it shows that the brain can alter the architecture of sleep according to what occurred earlier. Sleep stages are not simply produced according to a rigid schedule. They are dynamically regulated. The night is negotiating with itself. If one state has been reduced, later cycles may shift. If sleep pressure is high, deep non-REM sleep may become especially prominent. If sleep has already been plentiful, the pattern can change again. This flexibility helps explain why a daytime nap can sometimes affect the following night. A sufficiently long or late nap reduces some homeostatic sleep pressure before bedtime arrives. The internal clock may still say that nighttime is approaching, but the brain's accumulated need for sleep is smaller. Two major systems are now giving slightly different messages. The circadian system says that this is an appropriate biological time to sleep. The homeostatic system says that some of the pressure has already been relieved. That difference can make falling asleep take longer. It can also change how deeply the early part of the night unfolds. This interaction occurs every day, even when the schedule is perfectly ordinary. During the morning, sleep pressure is relatively low after a night's rest. As wakefulness continues, it builds. At the same time, the circadian system produces a changing drive for alertness. For much of the day, that circadian alerting signal helps counter the growing pressure to sleep. This is one reason you do not normally become progressively sleepier every single hour from breakfast onward. The two systems partly oppose each other. Toward the usual bedtime, the balance changes. Wake-promoting circadian signals weaken, while accumulated sleep pressure is high. Sleep becomes easier to enter. Then the entire relationship reverses overnight. Sleep pressure declines. The circadian system moves through biological night, and toward morning, the increasing drive for wakefulness begins to meet a brain that has already discharged much of its accumulated need for deep sleep. What feels like a simple night of unconsciousness is actually a constantly changing equation. The brain is measuring where it is in the 24-hour cycle, while also responding to how long it has been awake. Even the depth of individual regions can reflect recent experience. Areas of cortex that were especially active during the day may show stronger local slow-wave activity during subsequent sleep. This has led researchers to think of sleep pressure as partly local rather than entirely uniform. The brain may not require exactly the same amount of recovery everywhere. A network heavily used for a particular task, may enter the night with a slightly different history from a network that was less engaged. Again, this should not be imagined as tiny independent brains sleeping separately inside the skull. Sleep remains strongly coordinated across the nervous system, but local differences suggest that the night's slow rhythms may respond to how individual circuits were used before sleep began. In this way, waking life leaves traces in sleep even when those traces never become dreams. A demanding day can influence the intensity of slow waves. A long period without sleep can alter the structure of the next night. A nap can reduce later sleep pressure. Interrupted. REM can change subsequent REM expression. The brain continuously adjusts, and while all of this regulation is happening, you experience none of the calculation. There is no meter showing that sleep pressure has fallen by half, no sensation that one stage has been given priority. No awareness that certain cortical networks are producing stronger slow rhythms than others. You simply sleep. Then, eventually, the need that felt overwhelming the night before has been partially relieved. The same bed that seemed irresistible at midnight may feel unnecessary after morning arrives. The brain has quietly changed its own relationship with sleep, and perhaps that is one of the most curious things it does during the night. Sleep does not only restore the body, it gradually removes the very pressure that made sleep necessary in the first place. Another strange feature of sleep is that the brain does not simply become less responsive to the world. It becomes selective about what deserves to interrupt the night. This selectivity is surprisingly sophisticated. Imagine two sounds reaching a sleeping person at roughly the same volume. One is meaningless and familiar, perhaps the quiet hum of air moving through a vent. The other is unusual, emotionally important, or personally relevant. The physical energy entering the ears may not be dramatically different, but the sleeping brain can treat the two signals very differently. Part of this happens because hearing does not stop when the eyes close. Sound waves still move the eardrum. The tiny bones of the middle ear still transmit vibration. The cochlea still converts those vibrations into neural signals. Information continues traveling into the brain. What changes is how far that information is allowed to spread, and what the nervous system does with it. During sleep, the brain can still detect changes in tone, timing, repetition, and familiarity. Some research suggests that meaningful speech may be processed more strongly than meaningless or highly predictable sounds, even when the sleeper never becomes consciously aware of hearing anything. This does not mean the sleeping brain is secretly listening to every conversation in the room. Complex comprehension is reduced, and much incoming information never reaches full awareness. But the system is not deaf. It is quietly evaluating. One of the clearest examples involves a person's own name. A familiar name has been repeated thousands of times across a lifetime. It is deeply associated with attention. When someone says it during waking life, the brain tends to treat it as significant, even when you are not deliberately listening. Some of that special status can survive into sleep. Measurements of brain activity suggest that personally meaningful sounds, including one's own name, can sometimes produce stronger responses than neutral stimuli. The sleeper may remain completely still, no eyes open, no memory forms. Yet something inside the nervous system has marked the signal as different. The voice delivering the sound may matter too. An unfamiliar voice can sometimes provoke greater processing than a familiar one. From an evolutionary perspective, this makes intuitive sense, although the exact neural mechanisms are more complicated than a simple danger detector. A familiar nighttime environment contains many predictable signals. A new voice may represent a change. And change is one of the things the sleeping brain seems designed to notice. The same principle helps explain why someone can sleep through repeated noises and then awaken when those noises suddenly stop. A ticking sound may become part of the expected background. The brain reduces its response. Then the rhythm disappears. The absence itself becomes unusual. Silence can be the surprising event. This tendency is related to habituation. When a harmless stimulus repeats again and again, the nervous system often reduces its response to it. Habituation happens while awake, but forms of it also appear during sleep. Without such filtering, stable environments would be almost impossible to sleep through. Every distant engine, heating system, floorboard creak, or passing car would continually demand attention. Instead, the brain gradually learns what can be ignored. But this filtering is never perfect. The threshold for waking changes throughout the night. Deep, non-REM sleep generally requires a stronger stimulus to produce awakening than lighter sleep. Later in the night, when sleep contains more light, non-REM and REM, and homeostatic sleep pressure has fallen, some people become easier to wake. This means the exact same sound might be ignored at 1 hour and wake you at another. The world has not changed. Your brain state has. Even when a sound fails to wake you, the body may react. Heart rate can shift briefly. Electrical activity in the brain may show a transient response. Muscle tone can change. A sleeping person might adjust position or make a small facial movement. In this way, the body can acknowledge an event without inviting consciousness back into the room. Smell behaves differently. Compared with sound, odors are often relatively poor at producing rapid awakenings. The olfactory system remains capable of processing chemical signals during sleep, and odors can influence physiology or sometimes affect the emotional quality of sleep experiences. But to smell something new does not necessarily wake a person as reliably as a sudden meaningful sound. This is one reason smoke alarms are designed around loud acoustic signals, rather than expecting odor alone to wake someone. The sleeping sensory system is not equally vigilant through every doorway. Light follows yet another path. Even with the eyelids closed, enough light can pass through them to influence biological systems. The retina contains specialized cells that help regulate circadian timing and respond to environmental illumination. They are not used only for forming visual images. Light information can influence the body's clock even when you're not consciously looking at anything. This means the sleeping person can be affected by dawn before seeing dawn. As morning light gradually increases, signals from the eyes can reinforce the body's transition toward daytime physiology. The outside world begins shaping the coming morning before visual awareness returns. Touch can also produce remarkably specific responses. A blanket slipping away may cause a sleeper to pull it back. A limb reaching the edge of the mattress may change direction. A partner shifting nearby may prompt a small repositioning. These actions can look deliberate, but they may occur with little or no conscious awareness. The brain is using incoming sensory information to maintain comfort while preserving sleep. It is not solving the problem with words. There is no internal sentence saying, "The blanket has moved, and I should retrieve it." A much older layer of nervous system control is enough. The same applies to pressure. When one part of the body remains compressed for too long, sensory signals from skin, muscles, and joints gradually change. Eventually, a repositioning movement may occur. The sleeper rolls slightly. Weight shifts, blood flow changes, pressure is redistributed, then stillness returns. This automatic movement protects comfort without requiring a remembered awakening. Balance and body position are also monitored in the darkness, even lying down. The brain receives information from the vestibular organs of the inner ear and from receptors in muscles and joints. These signals help maintain a basic model of where the body is located. That model can occasionally become distorted in your sleep. The sensation of floating, tilting, shrinking, or falling during the transition into sleep may partly reflect unusual interactions among systems that normally agree about body position. When visual information disappears and waking control weakens, the brain's internal map of the body can become briefly unstable. This may be one reason. Sleep onset sometimes feels physically strange, even when the body itself has barely moved. The deeper lesson is that sleep does not remove the body from the world. It changes the rules of access. Sound continues. Light continues. Pressure continues. Temperature continues. The inner ear continues sensing orientation. The skin continues reporting contact. The brain simply becomes much more selective about which signals are allowed to become part of conscious experience. Most are quietly processed and dismissed. Some trigger an adjustment. A few are judged important enough to wake you. And because almost none of this is remembered, morning creates the illusion that the world stopped reaching you after your eyes closed. It did not. For the entire night, the sleeping brain remained connected to the room. It just listened differently. Some of the changes produced by sleep do not become obvious until the next day. You wake, begin moving through the morning, and only then does the brain reveal that the night has quietly altered the way it responds to the world. One of the clearest examples involves attention. Staying awake requires far more active regulation than it feels like. While you are alert, the brain continually decides what deserves focus and what can remain in the background. Conversation is followed. A moving object is noticed. An irrelevant sound is ignored. A thought is held in mind long enough to finish a task. These abilities depend on networks distributed across the frontal and parietal regions of the brain, as well as deeper systems involved in arousal. After adequate sleep, those networks are generally better prepared to maintain stable attention. After prolonged wakefulness, attention becomes less consistent. The strange part is that fatigue does not always produce a smooth decline. You may perform normally for a while and then have a brief lapse. For several seconds, concentration weakens dramatically, then it returns. This suggests that the tired brain can fluctuate between stronger and weaker states of responsiveness. Sleep helps restore the stability of those systems. In laboratory tasks, one of the most reliable consequences of insufficient sleep is greater variability in reaction time. A person may respond quickly to many signals and then suddenly respond much more slowly to one. That single lapse can occur without the person realizing how much their attention briefly deteriorated. Sleep, then, helps preserve not only how fast the brain can respond, but how consistently it can remain ready. The frontal regions involved in judgment and self-control are also strongly affected by sleep loss. This matters because the brain must constantly balance immediate impulses against longer-term goals. Should attention remain on the current task or shift towards something more interesting? Should a small irritation be ignored or reacted to? Should a decision be made now or delayed until more information arrives? These choices require coordination among several networks. After a sufficient night of sleep, that coordination generally functions more effectively. When sleep is restricted, people may become more impulsive, less flexible, or more likely to rely on simpler decisions. The sleeping brain has therefore influenced choices that seem completely unrelated to sleep. Another overnight effect appears in the way emotional signals are handled. A human face contains a remarkable amount of information. Tiny changes around the eyes or mouth can suggest happiness, anger, fear, uncertainty, or fatigue. The brain analyzes these signals rapidly, often before conscious thought catches up. Sleep quality can influence how accurately and calmly this emotional information is processed the next day. After insufficient sleep, emotionally negative or ambiguous signals can sometimes receive stronger responses. One brain region frequently involved is the amygdala, which helps evaluate emotionally important information. The amygdala does not operate alone. During waking life, it communicates with frontal regions that help place emotional reactions into context. Adequate sleep appears important for maintaining this balance. When sleep is seriously restricted, communication within these regulatory networks can change. An ordinary inconvenience may then feel more significant than it otherwise would. A neutral expression may be interpreted less accurately. Patience may become harder to maintain. This does not mean sleep determines mood in a simple or predictable way. Human emotion depends on circumstances, personality, health, relationships, and many other factors. But sleep changes the biological conditions under which emotion is regulated. A quieter night can influence a louder day. Sleep also affects how the brain evaluates rewards. When tired, the appeal of immediate rewards can increase. Food may seem more tempting. Novel experiences may attract more attention. The effort required for a task may feel larger. Some studies suggest that reward-related brain circuits respond differently following sleep deprivation. Again, the effect varies from person to person. But the broader pattern is intriguing. A biological state that occurred hours earlier can change the apparent value of something placed in front of you now. Sleep may also help the brain detect patterns that were difficult to see during waking practice. Imagine learning several examples that share an underlying rule. At first, each example may feel separate, after time, and sometimes after sleep. The common structure can become easier to recognize. Research into this kind of abstraction suggests that sleep may sometimes support the extraction of broader patterns from recently learned information. The evidence depends heavily on the task, and sleep does not guarantee sudden insight. But the possibility fits with what is already known about memory reorganization. During the night, information may become less tied to the exact form in which it was first encountered. Connections can emerge between experiences that were originally stored separately. This may help explain why a difficult problem occasionally feels different in the morning. The phrase, "sleep on it," has existed far longer than modern neuroscience. It would be an exaggeration to say that the sleeping brain secretly solves every problem placed before it. Most difficult problems still require deliberate waking thought. But sleep can change the memory landscape in which that thought occurs. Some information becomes easier to access. Irrelevant details may become less dominant. Relationships among ideas may become clearer. When the problem is considered again, the brain is working with material that has been subtly reorganized. Creativity may benefit from similar processes. Creative thought often depends on combining information that was previously separated. A familiar concept is linked with an unexpected one. A distant memory becomes relevant. A pattern is recognized across two apparently unrelated experiences. Sleep, particularly through its effects on memory organization and associative processing, may sometimes support these connections. REM sleep has attracted special attention in this area because its neural environment favors unusual associations. and vivid internally generated imagery. But researchers are still debating exactly which stages contribute most strongly to different forms of creative insight. The safest conclusion is not that REM creates creativity. It is that a full night's changing sequence of sleep states can influence how previously learned information is represented and connected. Even language may benefit from these overnight changes. When people learn new words, the unfamiliar information initially competes with words that have been known for years. After consolidation, new vocabulary can become more smoothly integrated into existing language networks. Sleep has been associated with parts of this process. A word learned yesterday may begin to behave more like an ordinary part of the mental dictionary after sufficient time and sleep. Again, nothing announces that this transformation is happening. There is no moment during the night when the sleeper feels a new word being moved into place. Morning simply reveals that retrieval has changed. This is a recurring theme in sleep science. Many of sleep's effects are invisible while they occur. The night changes something quietly. Then waking life exposes the result. Attention is steadier. A skill feels more natural. A memory is easier to retrieve. An emotional reaction is easier to regulate. A pattern becomes more obvious. Or an idea that felt stuck the previous evening becomes slightly easier to approach. None of these outcomes belongs to sleep alone, but sleep helps create the conditions in which the waking brain can operate effectively. The sleeping mind may seem removed from the world, yet hour by hour, it is preparing the brain for the moment when the world returns. While the sleeping brain becomes less interested in the outside world, it remains intensely attentive to something much closer. The chemistry inside the body. Every second of the night, invisible measurements are being made. The concentration of carbon dioxide in the blood changes slightly from breath to breath. Oxygen rises and falls within a narrow range. Acidity shifts by tiny amounts. Blood vessels stretch with each pulse. The lungs inflate and empty. None of this produces conscious awareness under ordinary conditions, yet the nervous system is continuously reading these signals and adjusting the body in response. Breathing offers one of the clearest examples. When you are awake, respiration is partly automatic and partly voluntary. You can deliberately take a deep breath. You can hold your breath for a short time. You can change breathing to speak, sing, laugh, or sigh. Once sleep becomes established, much of that voluntary influence disappears. Automatic respiratory control takes over more completely. Neurons in the brainstem generate the basic rhythm. Other sensors continually check whether that rhythm is keeping the body's internal chemistry within acceptable limits. One of the most important signals is carbon dioxide. Every active cell produces carbon dioxide as part of normal metabolism. It travels through the bloodstream to the lungs, where it can be exhaled. If carbon dioxide begins to rise, the chemistry of the blood and fluid around the brain changes slightly. Specialized chemoreceptors detect this change. The respiratory system responds by adjusting ventilation. Breaths may become deeper. They may become more frequent. Carbon dioxide is removed more rapidly. All of this can happen while you remain completely unaware that any correction was needed. Oxygen is monitored as well. Sensors located in structures called the carotid bodies near major arteries in the neck are particularly sensitive when blood oxygen drops significantly. They send information toward the brainstem, helping regulate breathing and cardiovascular responses. So even during deep sleep, The nervous system maintains a continuous chemical conversation with the bloodstream. The body is asleep. Its internal monitoring system is not. Interestingly, the sensitivity of breathing control changes somewhat when sleep begins. Carbon dioxide levels commonly rise slightly compared with wakefulness because ventilation becomes a little lower. This is usually a normal feature of sleep physiology. The respiratory system settles into a different operating range. It is a small example of something that happens repeatedly across the body at night. The sleeping body is not merely performing daytime physiology more slowly, it often adopts a slightly different set of normal values. This applies to circulation as well. Each heartbeat stretches the walls of major arteries. Embedded within those vessels are pressure-sensitive receptors known as baroreceptors. They help detect moment-to-moment changes in blood pressure. If pressure suddenly rises, signals travel toward the brainstem and can help slow the heart or alter blood vessel tone. If pressure falls, compensating responses can move in the opposite direction. This feedback system continues while you sleep. You never need to know your blood pressure in order for your nervous system to regulate it. Even when dreams are occupying the mind, deeper circuits are measuring every pulse. The vagus nerve plays an important role in this nighttime physiology. It carries signals between the brain and many internal organs, including the heart and digestive system. During stable non-REM sleep, parasympathetic influences associated with vagal activity often become more prominent. This helps support the generally calmer cardiovascular pattern of that stage. Yet the balance can change rapidly. A brief arousal may produce a burst of sympathetic activity. The heart accelerates while raw blood vessels adjust, and the body settles again. These changes can be remarkably fast. A sleeper may move from a quiet cardiovascular state to a brief surge of activation and back again, without forming any memory of the event. Blood itself also follows nighttime rhythms. Different components of the blood do not remain at exactly the same concentrations across the day and night. Hormones alter fluid distribution. Posture changes the way water moves between tissues and the circulation. Kidney activity changes. The long period without drinking slowly alters hydration. Even lying horizontally affects circulation differently from standing. During the day, gravity pulls fluid toward the legs. When you lie down, some of that fluid redistributes toward the upper body. The kidneys and cardiovascular system detect the change and adjust. This is one reason nighttime physiology cannot be understood only as the absence of daytime activity. Simply changing from upright to horizontal alters the physical problem the body must solve. The lungs experience this change too. When standing, gravity creates differences in ventilation and blood flow from the upper to lower parts of the lungs. Lying down changes those relationships. The diaphragm also sits differently because abdominal organs shift slightly with position. Your breathing system therefore spends the night operating in a geometry different from the one it uses while you walk around during the day. Body position can further alter this geometry. Sleeping on the back, side, or stomach changes the distribution of pressure across the chest and abdomen. It changes the shape of the upper airway. It changes how gravity acts on the tongue and soft tissues of the throat. It can subtly affect where air and blood move through the lungs. The sleeper may change position without understanding any of this. The nervous system responds only to the consequences. If one position becomes uncomfortable or breathing becomes less stable, movement may follow. Another hidden regulator is blood glucose. Although you stop eating for many hours, glucose does not simply fall continuously until breakfast. The liver helps maintain it by releasing stored glucose and producing new glucose when necessary. Hormones coordinate this process so that the brain and other tissues continue receiving fuel throughout the overnight fast. Near morning, hormonal changes can alter glucose regulation even before food arrives. The body is gradually moving toward its daytime metabolic state. This means breakfast is not the event that switches metabolism back on. Metabolism never switched off. By the time you wake, the internal chemistry of morning has already begun. Electrolytes are also continuously regulated. Sodium, potassium, calcium, and other charged particles are essential for electrical activity in nerves and muscles. Their concentrations must remain within tightly controlled ranges. Kidneys, hormones, and cellular transport systems continue managing these ions all night. Every dream, heartbeat, muscle twitch, and slow brain wave ultimately depends on tiny movements of charged particles across cell membranes. The experience of sleep may feel weightless and abstract. At the physical level, it is built from chemistry, billions upon billions of ions moving across microscopic boundaries. Molecules binding to receptors, gases dissolving into blood, pressure sensors stretching, chemical detectors firing, organs answering signals they never consciously receive. The strange contrast is almost perfect. Your conscious world may contain a dream of walking through an unfamiliar city, speaking with someone who does not exist, or floating somewhere impossible. Meanwhile, beneath that imagined world, the body remains firmly occupied with reality. How much carbon dioxide is present? Is oxygen sufficient? Is blood pressure stable? Is enough glucose available? Is fluid balance changing? Does breathing need to deepen? Does the heart need to speed up or slow down? These questions are never asked in words. They are answered automatically, second after second, throughout the night. And because the corrections are usually so precise, you wake with no idea they ever occurred. Sleep can feel like surrendering control. Physiologically, it is almost the opposite. As conscious control fades away, older and quieter systems take over, keeping the chemistry of life within narrow boundaries until awareness is ready to return. By the final part of the night, sleep has become a different landscape from the one you entered hours earlier. The long stretches of deep, slow-wave sleep that were especially prominent near the beginning have usually become shorter. REM sleep occupies more of the remaining cycles. The brain is moving more frequently through states that are closer, in some respects, to waking activity, and somewhere beyond the closed eyelids, morning may already be beginning. This is one reason dreams remembered near waking can feel unusually vivid. Later REM periods are often longer than those earlier in the night, giving internally generated experiences more time to develop. A dream may seem to contain a complete setting, several people, a sequence of events, and a strong emotional atmosphere. Then something subtle changes. Perhaps a sound reaches the brain. Perhaps the current sleep cycle naturally approaches an awakening. Perhaps increasing morning light strengthens the circadian signal toward wakefulness. The dream begins to lose its hold, and one of the strangest transitions in human experience takes place again. The brain replaces one reality with another. Only moments earlier, the dream environment may have seemed unquestionable. There was somewhere to stand. There were objects to see. There may have been a problem to solve or a person to speak with. Then the eyes open. Visual information from the actual room floods back into the system. The brain rapidly identifies edges, distances, familiar objects, and the orientation of the body. The dream world can collapse almost immediately. A bedroom becomes more convincing than the place that existed in the mind only seconds earlier. This reconstruction of waking reality is so fast that we rarely appreciate how much processing it requires. The visual system has to adjust to real light again. Auditory information must be anchored to actual sources. Touch from the mattress and bedding becomes conscious. The vestibular system contributes information about orientation. Memory provides the larger context. This is my room. It is morning. I was asleep. That last recognition may seem obvious, but it depends on the brain reconnecting the present moment with an autobiographical story that was largely suspended during sleep. Personal identity itself returns smoothly. You do not normally need to relearn who you are each morning. Networks containing knowledge about your life, relationships, plans, and surroundings become available again as waking consciousness stabilizes. Within seconds, an enormous amount of context is restored. The body also changes its motor state. If waking occurs from REM sleep, the strong inhibition affecting many skeletal muscles must disappear. Voluntary movement becomes fully available again. A hand can reach toward the blanket. The head can lift. The legs can support the body. The motor system that was largely prevented from acting out dream movement now reconnects with deliberate intention. Usually this happens so smoothly that it is invisible. You simply decide to move, and movement is possible. At the same time, sensory thresholds are dropping. Sounds that might have been ignored a few minutes earlier now become difficult not to notice. Traffic outside, a bird, a voice in another room. The movement of fabric, the quiet mechanical sounds of the home. The environment has not necessarily become much louder. The brain has become more available to it. This change shows once again that awareness depends not only on what reaches the senses, but on the state of the system receiving it. Morning also restores a different relationship with gravity. For hours, most of the body has been supported horizontally. Then you sit up. Fluid distribution begins changing. The cardiovascular system must respond as gravity pulls blood downward. Blood vessels adjust their tone. Heart rate may shift. Mechanisms that maintain circulation perfectly well while lying down now have to adapt to an upright body. Then you stand. Within moments, a sleeping organism has become a walking one. Muscles that spent the night largely free from postural work begin stabilizing the ankles, knees, hips, spine, neck, and head. Balance systems become more active. Vision participates in orientation. The brain coordinates hundreds of muscles to perform something as ordinary as crossing the room. The transition feels simple, only because the nervous system is so practiced at doing it, and yet the night is not completely gone. Its effects continue into the waking brain. A fragment of a dream may still be present. A feeling may remain without an explanation. A memory learned yesterday may now be slightly easier to access. Attention may feel restored. Sleep pressure has fallen. The hormonal environment has shifted. Body temperature is rising toward its daytime range. Metabolism is moving toward the pattern associated with activity and feeding. The body that wakes is continuous with the one that fell asleep, but is not physiologically identical to it. Hours of changing brain states have occurred in between. This may be the deepest strangeness of sleep. From the inside, so little seems to happen. You remember closing your eyes. Perhaps there are scattered dreams. Then morning appears, but hidden within that apparent gap, the brain and body have passed through an extraordinary sequence of events. Electrical rhythms have changed again and again. Deep, slow waves have moved across the cortex. Brief spindles have appeared. Muscles have relaxed and, during REM, many have been temporarily inhibited. Eyes have moved beneath closed lids. Breathing has shifted between stable and irregular patterns. The heart has changed its rhythm. Blood pressure has risen and fallen. Heat has moved from the core toward the skin. Hormones have followed their nightly schedules. Memories have been reactivated, altered, strengthened, weakened, and connected with older knowledge. The brain has continued evaluating sounds from the room while constructing worlds of its own. The body has changed position without asking permission. It has swallowed, breathed, regulated fluid, maintained tissues, adjusted circulation, monitored blood chemistry, and protected a stable internal environment. And almost all of it has happened beyond conscious awareness. Sleep can look like inactivity only when viewed from the outside. Inside, it is a carefully changing biological state, not a pause from life, but another form of living. Perhaps tonight, when you notice yourself beginning to drift, you can think about that strange boundary for a moment. The room will slowly become less important. Thoughts may lose their edges. Sounds may seem farther away. At some point, without knowing exactly when, you will stop keeping track of time, and your awareness will quietly release the night. But nothing needs to be managed consciously. Your breathing already knows what to do. Your heart knows how to continue. Your internal clocks are still keeping time. Your brain will move through its familiar rhythms, whether you watch them or not. There is no need to follow every process. No need to notice the moment sleep arrives. Soon, even the idea of staying aware may become less interesting. The hours ahead can unfold without explanation. And while you sleep, hidden beneath the quiet surface, the extraordinary nighttime work of the brain and body will simply continue.